In this video, we'll continue our discussion of line integrals through conservative vector fields. So we have this vector field, and then this path. I drew the path because we did this one recently, and I think it's kind of neat. It started making sense to me why it's a tilted ellipse. So maybe you should check that out. And they're running it from 0 to 2 pi. The whole point here is we're going to run from some point. I'm just going to put it here and all the way around to that same point. So we're going to figure out, and you're going to like this when this happens because it's going to save you some work, but it has to be a conservative vector field for us to make this claim. So first things first, let's show that it is a conservative vector field. So M, and we'll do N. So I just switch my variables, Y and X. Then I'm going to do M and P, and I switch those variables. And then the last one I haven't done would be M and N, M and P. We need N and P. So it's going to be a Z and then P with a Y. Cool. We have to check each one of those. These go pretty quick. M with respect to Y is 1. N with respect to X is 1. M with respect to Z is -1. P with respect to X is -1. N with respect to Z is 1. And P with respect to Y is 1. All right, cool. That tells us that F is conservative. All right. Now, I'm going to make a point here. This didn't list out point to this point. It just said, that path from 0 to 2 pi. But if you notice, okay, let's call this point A. If I plug in 0 into this function, cosine of 0 is 1, sine of 0 is 0, and then 1 again. And then if I plug in 2 pi, cosine of 2 pi, let's put a b here, even though you'll see what's going to happen. Cosine of 2 pi is 1, sine of 2 pi is 0, and cosine of 2 pi is 1. So we are going from point A to point B, which really is just point A. So we're going from the same point to the same point. Well, if I follow my work formula that we came up with in this section, since it is conservative, and if I can find a phi, I'm just going to do phi of A minus phi of A. The same term minus the same term is going to be 0. So this is a very, I think it's a neat property of conservative vector fields. This leads back to path independence. If I go from one point, I'm going to draw some points on my screen here. If I go from this point in a conservative vector field, and I go here, 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 and I come back around, and I end up back at the same point, that is the same as doing this much work. That is the same as putting a point, and I'm going to stand at this point, and my path is just going to be stopping at that point. I didn't move. That would be the same as all three paths in a conservative vector field when it comes to work. So, if you have a closed curve in a conservative vector field, the work is 0. And it's because of path independence. And it comes down to right here, right? We're going to plug in the same point, so it's just going to subtract itself because it's conservative. It's a very neat property that we have there. Okay, one last thing I'm going to put down here at the bottom. Very important. This double arrow thing just means that it can go both ways. Like if it's path, I just see see a typo here. There we go. You guys didn't see anything. Path independence. I'll fix that in your notes. Path independence is the same thing, or implies, not the same thing, implies f is conservative, which implies I can take that integral in that, we should probably finish off this thing here. This is phi of b minus phi of a, right? Given the potential function that makes f. So, path independence, f is conservative, and we also get this last theorem that we have worked through this section, all implying each other. That's what the double arrows mean.